Hello, everyone. Welcome to Rational Science, directly from Frankfurt, Germany. We have a good show today, and as we've been doing lately, we divide it up in three parts for those of you who are new here. And we start with extinction, pretty popular subject. Then we continue with physics. Today we're going to be dealing with recoilless emission, whatever that is. And then I'm going to be answering some questions and comments that people made since last time. Okay, so let's get on with it. The other day I was telling people that I almost canceled the class because I had pain in one of my teeth, and it was quite bad. I had that for 2 days, and I was able to give the class because I put an aspirin next to it, and that solved the problem to a good degree. And fellow says there, says they have herbal rubs for your gums. And Amazon for pain, coconut oil pulling might work. Well, I didn't have to do any of those. What happened was I went to the dentist, and he went in there and opened up something in my gum there. I guess at the teeth, not my gum, but something in my teeth and my tooth, and he put some dentist poison there to I guess uh, put the nerve to sleep or something, close it up, and he told me to come next week. He's going to pull the nerve out. So that's, I guess, the solution. But the thing is that when I was down there, I was thinking about extinction, and I'm saying, what's going to happen with those people who survive the upcoming extinction? There's going to be pockets, I think, everywhere on Earth where people will survive, groups, etc. And will they have dentists on board? Or they're gonna, if you get a toothache, you're gonna end up like this guy in the movie who Castaway or Marooned or whatever the movie was called, where he had to break his tooth with a stone. So yeah, you don't want to be caught after the extinction event, the collapse, essentially the economic collapse. You don't want to be out there and not have a doctor. See, we're so used to these things. You have a pain or something, well, you go to the dentist, you go to the doctor. I had an operation a couple years ago now on my prostate, and man, and they even pulled a stone out of there, and so that's pretty heavy stuff, pretty heavy operation. And imagine the end of the world. You don't have any doctors. I can't imagine how the Neanderthals, when they ran into trouble, broken foot or whatever, or maybe a toothache, how did they handle that? Anyways, think about that. You need to befriend a doctor for the end of the world, okay? Okay, I talked about Google, and they've been fined by France, $600 million, okay? And Google was not very happy about that. And someone says, according to the government, the problem with Google isn't that they're an evil multinational New World Order apparatus. It's that the old school multinational NWO apparatus isn't getting so much of the media dollar anymore. Your best interests are never at heart. Yeah, I think the issue with the real issue is whether we should tax the multinationals at a higher rate, because right now with this COVID thing, a lot of people, don't have income. They lost their jobs, and if the government doesn't collect from them, it's got to collect from someone else, and it's probably going to be from these big corporations which are making a killing, in fact. And so, the question is whether they should be shouldering a heavier load at this point. And again, will that stop the collapse where we're headed towards, as I say? No, it just may stretch a little more, a little less. But I think collapse of the global economy is assured. Okay, I don't think we can avoid it. Okay, talking about Neanderthals. One fellow says, wow, I've suspected that much of the Neanderthal hypocrisy was distant, a distant shot on the out of Africa model. I guess they are removing all suspicions and just coming out and saying it. Okay, and another fellow along the same lines, talking about, the out of Africa. He says if man came out of Africa, it probably was not to find food. Because that's what I'm saying. Cro-Magnon came from Africa, came over to Europe, and was able to enter Europe once the Neanderthals were gone. Okay, so that's my take on that. And he's saying they probably didn't come out for food. Okay, so what did they come out for? So they probably just got tired of African behavior like we see in South Africa and other parts of Africa we see today. The behavioral differences between Africans and Europeans can be seen pretty clearly in South Africa, for example. Yeah, the problem is people extrapolate what we have today to the past. Like the other day, one fellow said that the Neanderthals, he could not imagine a Neanderthal not raping a woman out there. They're thinking of in terms of what they see today. The question here is whether in the wild, a Neanderthal would sleep with someone that is not of his own species, us. We were not of the same species. So first you got to tackle the issue of species, and then you got to tackle the issue of in the wild. And this is something similar. The fellow is saying that behavioral differences. I don't think they cared too much about behavior in those days. You're talking about the Paleolithic, fellow. You're talking about people who are living at subsistence level. Out there in the jungle, they have to kill something to live one more day. This is what's on their mind, okay? And yeah, they do have sex, but hopefully with the right species, okay? But, it's very simple. Humans came out of Africa and went all the way to Asia, to China and Indonesia, and also went into Europe, because we do find footprints, and we have a partial skull bone that I showed the other day, female, about 400,000 years ago. They think it's Heidelbergensis type, okay? And so, there was someone already in England 400,000 years ago. We already have evidence that there's been a bipedal animal, monkey, gorilla, us, whoever, 800,000 years ago in England. And so we're finding these bones, these fossils, these skulls, and other bones as well, right, in Western Europe. And they date to, 800,000 million years ago, maybe. So we have to think that, at least Homo erectus, which is that level, was already in England or in France or in Germany, in that region. And where did he come from? Well, you have to assume that he came out of Africa. Okay, he had to come out of Africa, and this is the reason. Here you see the skulls that we have today. Homo habilis, he's 2.5 million years ago. He's got only 600 cubic centimeter capacity in his brain. And you can see how the brain grew over time. And we only find habilis in Africa. Erectus, we find them in different parts of the world, but more of them in Africa. And we have to assume that someone in the level of habilis, if it wasn't habilis himself, someone around that level gave birth to Erectus eventually. Erectus gave birth to Heidelberg in Europe, and you would have to think that Heidelberg gave birth to Neanderthal in Europe. That's what the fossil evidence seems to show. Okay, so this is my take on that. There is no level of habilis anywhere At least we haven't found any in the world yet, other than in Africa. And you might say, well, maybe they haven't found it, they haven't looked deep enough, or maybe we'll find habilis level in China tomorrow or whatever. Could be, but right now the evidence shows that habilis started in Africa. There is no habilis outside of Africa. That level of development, okay, of skull development. So we have to think that our species, at least our whole dynasty, if you want to call it that, started in Africa. Okay? Yes, that's my take on it, anyways. Fellow also says, also we can look at the cold ice records, because I was talking that Neanderthals did not wear clothes because they were born in the snow. They were born in the in Arctic weather. They didn't know what cold was. That was my argument last time. This guy picks up on that. He says, we can look at cold ice records of William Hoff. Yeah, he's talking about really Will Hoff, not William Hoff. That's not his name. His name is Will Hoff. Okay, the Iceman. The human tolerance for cold might be much greater than we think. Well, there's a difference between Mr. Will Hoff. This is him, by the way. Let me show you who this man is. Okay, they put him in ice, okay, the Iceman, and they throw all kinds of ice in there, okay, and the guy can withstand maybe 2 hours of this, okay. So he does this to disperse his, propagate his, or proselytize on his method. Okay, I guess he's got a business in which he tries to get people to think in terms of how they can withstand extreme cold. Okay, so he does these shows, freak shows, Barnum and Bailey type freak shows. And it's interesting here, you see his method, okay? He talks about breathing and cold therapy, okay? And it's interesting that while looking at this, I was seeing that he goes out into the cold and he goes out there with shoes. I mean, he does have shorts on, right? But he does wear shoes, okay? And I think that the main reason he wore shoes is that maybe he can stay in the snow, in the cold with his bare feet for a little while. I don't think he can stay there all day with his feet in the cold, okay? Especially if he's not running. That's another issue. If you're sweating because you're running, even though it's cold and it's in the snow, you can withstand it a lot more than if you're just standing still, on the snow. And I'm saying that all that is completely different than what Neanderthal was. This is Neanderthal taking a bath, in the winter cold in the snow. He could stay in there forever. Neanderthal was like the woolly mammoth. Woolly mammoth didn't use clothes. Polar bears don't use clothes today. Wolves don't use clothes. Penguins don't use clothes, and they have their feet. Showed this the other day. Their duck feet completely in the snow, and they're so used to it because they live in the snow. This fellow here, Will Hoff, he can't do that. And again, he's got to prepare, he's got to train him mentally and physically to withstand all this stuff. He can do it more, he can withstand it for longer periods than other people, common man out there who haven't practiced or whatever. We're not talking about the same thing. We're talking about a guy who was born, who's got it in his genes, who probably was a woolly guy like that guy there, and who lived in the snow. He had no reason to wear clothes. Okay, so clothes were not invented by Neanderthals, and again, we haven't found needles in any of their sites. We found all kinds of tools, weapons, different things that we found from them, but we haven't found any needles. You would think that, they would have to sew the garments together, the furs or whatever they were supposed to put on. No, these were gorillas, and any more than a gorilla puts clothes on in the African jungle. These fellows never had to use clothes at all. Okay, so and that would have been a distinguishing feature if humans met them, because humans moving into that region, I'm sure they started putting on clothes. And that's what you see really, that about 35,000 years ago, 36, maybe 38,000 years ago, about 2,000 years after the Neanderthals disappeared, which is around 40,000 years ago, humans came in there and they started, and we have some evidence that there were needles. So the needle appears, maybe around that time. And that would strike me as odd. But for a Neanderthal to find a needle in the Neanderthal haystack, good luck with that one. I don't think it'll ever happen. Okay, now the fellow says linear regression. He's quoting an article here, by the way, and he said linear regression of genetic complexity on a long scale extrapolated back to just one base pair suggests the time of the origin of life 9.7 billion years ago. And you might say, well, what's the problem with that? Well, the problem when we contrast that with the official version, the Earth is only 5 billion years old. Okay, so these guys are extrapolating, they're doing just some math there, and they're saying that it's almost 10 billion years ago that life started on Earth. And so where does that leave the origin of the Earth itself? Okay, did life start without the Earth? So he says life before the Earth. Okay, he's suggesting life came from abroad, not necessarily from the ETs coming here and visiting us. In a way, yes. In a way, no. He's talking about panspermia. Okay, that some kind of life eventually arrived on Earth, but life already was out there in the universe, maybe before that. But it says the word, this fellow just makes a comment, says they word it as extrapolated instead of predicted, in this case on tour, the solar system with, oh, okay, he's just mentioning the place. In other words, he's saying that they're just doing math. And that's true. One thing is just to do math. We have a lot of problem with that because they take a lot of the physical interpretations, they extrapolate them from math. And that doesn't always work so neatly, okay, for Mother Nature, especially Mother Nature who doesn't know anything about math. Okay, so here, when you go to that site, the one he mentioned, the paper, I went in there and looked at it. It says these are the main points they want to make in their paper. Life took approximately 5 billion years to reach the complexity of bacteria. Okay, there was no sign of intelligent life in our universe prior to the origin of Earth. Intelligent life, he's qualifying that. He's not saying there was life, but not intelligent life. Okay, intelligent life has begun appearing in our universe, has just begun. Okay, thus Earth could not have been deliberately seeded with life by intelligent aliens. Earth was seeded by panspermia. Now there was some kind of bug crawled out of a rock, and that's how we became impregnated with life here on Earth. That's what he's suggesting. Okay, talks about the Drake equation for guesstimating the number of civilizations in the universe is likely wrong. He's saying that Drake had it wrong, Frank Drake. I'll go over that in a second. The doubling of time of complexity has reached approximately 20 years. The predicted technology singularity talks about this paper talks about that as well. So the authors of this paper, they're talking about panspermia, the Drake equation, which has to do with what the possibility is of life being popular out there in the universe. How many civilizations could there be out there with life? That's what the Drake equation tries to figure out. And again, it's all mathematics, and the question is, can you extrapolate that into physics and say, oh yeah, I can safely say the following because of that math? And a lot of people criticize the Drake equation on that basis, that it all amounts to your assumptions, what assumptions you make for each one of the points that Drake has in his equation. And so here's the Drake equation, okay? Essentially, this is what Drake was trying to figure out, or what he suggests are the important points that anyone tackling the problem should address. Okay, rate of star creation in our galaxy, fraction of those stars that have planets. Okay, now I would think that all stars have planets. They're saying that they probably don't, and that we got to look at the fraction of stars that have planets. Okay, average number of planets that might support life per star that has planets. Not all planets are suitable for life. Okay, fraction of the above that actually go on to develop life, because even if they can, maybe they don't for whatever environmental reasons, right? Fraction of the above that develops intelligent life. Sometimes I wonder how much how much intelligence all these people have, right? Fraction of the above revealing their existence via signal release into space. In other words, even though they develop life, do they develop the capacity to transmit and receive that kind of thing, information? Lifetime of such a civilization wherein it communicates its signals into space. Okay, because then they might want to, but maybe their civilization dies too early. Maybe extinction reaches them for whatever reason, and so they don't get to communicate, even though they have the tools to be able to do so. Okay, so that's what the Drake equation talks about. Here are his values. This is what he calculated. Drake tried to calculate what percentage or how many stars there could be out there that have life, or planets that have life. And he says one star formed per year on the average over the life of the galaxy. He addresses point by point there. In other words, 1/5 to 1/2 of all stars formed will have planets. Stars with planets will have between 1 and 5 planets capable of developing life. 100% of these planets will develop life, 100% of which will develop intelligent life, and 10 to 20% of which will be able to communicate. I'm not sure why he made that distinction, but then he moves on to the last one. He says 1,000 to 100 million communicative civilizations. That's what he thinks. Okay, that's what he thinks should be out there. Is he maybe a little too optimistic? Okay, I think sometimes these fellows, again, do a lot of math and they don't pay attention to the physics of it. Okay? And what I'm referring to here is that all these folks, a lot of them, in this case, Drake, he had a PhD. He spent his entire life on this SETI thing, which he worked with Carl Sagan as well to send some evidence that we're alive here on Earth out into space with one of the probes. The question is there any possibility whatsoever of ever seeing or receiving information from another civilization? And the answer is no. There is no possibility whatsoever. These people are wasting their time, wasting money out there, trying to locate some sounds. It's like they don't know physics. They studied physics and they don't know physics. They don't know anything about it. All they do is math and extrapolate it from the math. There is absolutely no possibility whatsoever of receiving information from any other civilization. Are there out there? Yeah, I'm almost sure there have to be in the universe with so many planets and stars, and that they're out there. But life is a very scarce resource, and you can tell that just by looking at our solar system. We're the only planet developed life, and all the others are dead planets. They're really, I said it right. They're dead stars. That's what they are. But they didn't develop life, and you would think that with that life should be very common out there, and it's not. They looked at like 20 light years in the vicinity radius. None of the stars seem to have life of any kind. We haven't received any information or anything from those stars, from those regions. And you say, why could that be so? And I'll tell you why. The first one is that we've been around only 200,000 years here on Earth, us humans. And we've had technology to communicate maybe for only 100, 150 years at the most. Before that, we had no way of communicating anything. We had no notion of the light signals or electricity or magnetism in such a way that we could send information out of the earth. We only had that type of technology only 150 years. Now, 200,000 years, supposedly the time we've been on Earth, humans have been on Earth, that's a drop of water in the billions of years that even general relativity says we've been around. We've been around 14 billion years according to them. I'm saying we've been around forever. There's been no beginning to the universe. So here we are. 200,000 years is nothing. And that's when we were just hunter-gatherers for most of that time. We developed technology to be able to communicate outside the earth maybe 150 years ago. I'll give you 200 years if you want. 200 years. That's even a smaller, that's not even a drop of water in the ocean. That's absolutely nothing. And now look at the fact that we could be staggered. There's a civilization rising here. It dies, it goes away, it becomes extinct, and then suddenly we come up and we look around, we say, oh, let's look see if there's a civilization out there that can hear us and see us. Well, not only are we separated by time, we're separated by the scarcity of life to begin with. It's got to be maybe the third planet, third rock from the star, so to speak. It's got to be in the right place at the right time. Then, even if it develops a civilization, we're talking maybe 150 years in which they develop technology like we did here, and then we become extinct. And so even if, I mean, to match 150 years of their civilization with 150 years of our civilization in the universe, it's almost impossible. I would say it's so scarce, it's beyond calculations. I'm sure a mathematician will go out there and try to figure it out, but it's not even probable. It's impossible. So the question is staggering in development. All civilizations come to an end, extinction. So this notion that they developed, that there's all these levels, that civilization takes over the planet, then over the star, then over the galaxy, and so on, absolute nonsense. Yeah, absolute nonsense. These people see too much Star Trek, and they're not thinking enough time. Okay, one fellow tries to address the question that I ask always at the end, which is answer to the question of why the animals in the sea approximately died when the land animals died, because the sea animals were the food pyramid of the land animals, or maybe vice versa. And when one went, the other, one went too. So the dinosaurs ate fish, huh? No, I don't think so. I like the fact that you gave it a try at least, but at least I won't go with this theory. I don't think that's what happened. No, again, the mosasaurs, they ate ammonites, which ate probably zooplankton or both, just plankton of any kind, and not of any kind. They ate a special kind, and it was the kind that disappeared. Another plankton came up, like the grasses came at the end of, from the middle of the Cretaceous towards the end of the Cretaceous. You know, the angiosperms covered the land. They displaced the conifers. And somewhat like that, what you have in the seas is the same thing. The small plankton replaced the big plankton. And the ammonites ate plankton, the big plankton, the ones they were used to. And what ate them were the mosasaurs. That's just one food chain, just for reference. And so I don't think any of those were involved with the land dinosaurs, T-Rexes and whatever. No, one had nothing to do with the other. Okay? So no, I don't subscribe to this fellow's theory, but nice try. Okay, one fellow quotes several different papers, and they all say essentially the same thing, that none of the dinosaurs ate angiosperms. Okay, So he just put three different references saying that none of them ate angiosperms. They all ate conifers. There's no evidence that dinosaurs ate angiosperms. I read one paper once, I think it was from an Indian fellow, and this fellow argued that he found coprolites, or I can't remember really what, but he had evidence that one dinosaur at least ate angiosperms. And again, he was criticized by a lot of his peers. I don't think we really have any evidence that dinosaurs ate angiosperms. I don't think we'll ever have that evidence. And are going to try to stretch the evidence that they see or interpret it in such a way as to fit the angiosperms into the mouths of dinosaurs, because that would be a big hit. He'd get his name in lights. I don't think it'll ever find that because, again, dinosaurs radiated with the conifers. And here they were around for millions of years, not only in the Jurassic, but then again in the Cretaceous. And towards the end, when the conifers were dying out in the last half of the Cretaceous, maybe 60 million years, they gradually were going away, all the conifers, and they were replaced by the angiosperms, which is what the mammals grew or radiated with. So I think that's really what happened. The angiosperms muscled aside the conifers, which meant that the dinosaurs, because they ate conifers, were muscled aside as well. Only because the forests were shrinking, the jungles were shrinking. Jungles of cycad likes, Williamsonias, and other types of plants that they ate, those were disappearing. The forests, the jungles were becoming smaller and smaller, and the ground was being taken over by these weeds, which is what we eat today, the angiosperms. That's a better solution to extinction than saying that an asteroid hit the Earth. Okay. And along the same lines, the fellow says, yeah, it looks. He says that it looks that these people are trying to prove it at all costs that the dinosaurs ate angiosperms, but they have no way of proving it. They have found no evidence so far. But what a lot of people are noticing in the paleontology world is that what it says there, the new work helps confirm another recently published and controversial claim that most dinosaurs were already in decline 40 million years before the meteorite struck and finished them off. Yeah, I don't think there was a meteorite or asteroid that finished them off. It has nothing to do at all whatsoever with the extinction of the dinosaurs. The dinosaurs were already underway out. And it was a gradual disappearance. And if you're going to talk about a gradual disappearance, well, I think a good bet is that plants were going away, plants that they ate. Dinosaurs cannot change at the last moment and say, oh, I'm going to switch over to angiosperms because I cannot find enough conifers. It doesn't happen in the wild, okay? Especially if you've got millions of years of conditioning to a certain type of food. Millions of years, dynasties after dynasties after dynasties, and the last dynasty says, oh, I can't find conifers, I think I'll start eating magnolias or roses. It doesn't happen. Again, rabbits don't switch overnight from lettuce to pine leaves, okay? They don't like them, and I don't think you would either. But you tried, you showed us the experiment. Do the experiment. You say, tomorrow I'm not going to eat tomato, I'm not going to eat lettuce, I'm not going to eat any of that stuff. I'm going to start eating pine leaves. Yeah. Show us. Okay, again, final, always try to do Extinction 101 before 102. 101 is mass extinctions of the past. Okay, then you can always move on to human extinction. Because if you can figure out how it happened in the past and how the animals died in the past, maybe you can extrapolate that mechanism to us today and find out whether we can overcome that same mechanism, whether our intelligence, our technology, our ability to foresee events and take action, whether that has anything to do, whether that is an antidote to extinction, whether you can do something about extinction. and I'm saying we cannot. Okay? And again, the good question here is this one, the key extinction question. Why do the animals on land disappear more or less at the same time as the animals in the seas? That's the question you really got to answer, okay? And again, if you can answer that, it'll give you a pretty good clue as to why these animals disappeared. And if you can figure that out, you can probably figure out how they became extinct and extrapolate that mechanism to us. That's why I like that question. I think it's a key question. Okay, let's move around to the physics part. And we're going to be doing what? We're going to be doing recoilless emission, whatever that is. Okay, here's a quick recap of what we did these weeks, and we've looked at quantum mechanics, the mysterious, unexplained, that's why they're mysterious. They're mystical, right? Properties. And we took it about decoherence, okay, like for example in the slit experiment, the particles would be in phase all along, or the wave would be in phase, but it interacts with the environment, and because of that it goes out of phase, and that's that decoherence phenomenon that they've noticed in the lab. Can they explain it? No, they can't. They just say it is so. Entanglement, one particle over here affects another one over there, one far away from the other. How do they do that? They don't know. They can't explain it. They just say it does so. It's a fact. Okay, superposition, one particle vibrates, the other one doesn't vibrate. It's the same particle. How can one particle vibrate and not vibrate at the same time? Can you explain it? They say, no, we can't. It is so. God ordained it. It is so. That's what happens. These are the explanations they give you. These are all the physical interpretations, the names for each of those physical interpretations. Schrodinger's cat, the cat is both dead and alive until you peek inside the box. It's got to do, all of these essentially have to do with dualities. The mathematicians love dualities because in a way, it helps them cover every base. They can say, well, why this? Well, this is because of A, and why that? That's because of B. But A is a contradiction of B, but they use both simultaneously, and they call that duality, and they love these things. Okay, complementarity, light is both a particle and a wave. They say it behaves. It's the same thing, because when you say it behaves as such, you are in essence simulating here as a particle and here as a wave. Okay, so they're saying depending on the experiment that you run, that's the way they sweep it under the rug, the problem. No, the problem is you cannot say that light is both a particle and a wave, and that when you measure or you do something, it collapses to one or the other. You can't do that. Not in science, maybe in religion. Uncertainty, the ball stands still, and when it stands still, you know very little about its motion. And when it's moving, you know very little about its standing still, its location. Right? Again, dualities, contradictory dualities, okay? And they love these things. You know, they say, oh, it gives us something to think about. Spin. Spin, what is the problem with spin? Spin is not spin. That's the problem with spin. Okay? Spin is not spin. Spin is some kind of orientation of some kind, and they measure at that. It's like chopping light or the electron at that point and saying, oh, it's pointing in that direction. But they use the word spin because they want to give you the notion that this thing is twirling around like a top, and that's what they're going to use when you say, well, but is it twirling around like a top? Is that what you're telling me? No, it ain't. It's standing still. We measure and we say that's half spin, that's minus half, that's 1, that's 0 spin. They give you all these numbers for orientations or tilt of the spin, whatever that is. So hopefully you understood it all. So all these are unexplained properties. That's all they are. They just say it is so, we don't understand it, but it happens and we can use it for technology. And that's why they use the word quantum as an adjective for everything. Quantum dot, quantum computer. Why? Because they're going to be using the phenomena which they don't understand or can't explain and they're going to use that to say, well, we use the effect in technology, in the computer. Oh yeah, great. You can use it. It's like saying, I'm going to use a magnet to pick up iron filings. You don't know how it does it, but I can use that for something, because here I can use a magnet to pull something out, like a car in a wrecker yard. Okay, so you can pull it and you say, okay, I can use it, technology. Can you explain it? Oh no, I don't know how Mother Nature does that. That's the issue. The issue is that's where you have to break your brain, because hopefully Mother Nature doesn't do these things with nothing. Hopefully she does it with something which is invisible and intangible. And that's what magnetism, light, gravity, that's what all those are. They're invisible and intangible mediators. We can't see them, we can't touch them. And these people hope to see and touch them by running an experiment in the lab. That's the problem. Okay, and today we're going to do recoilless emission. What the hell is recoilless emission? Okay, here's, you've seen this maybe somewhere when you look at a crystal lattice, any crystal for that matter. Well, you say, well, it doesn't move, but it does. It does to some degree, and what they're saying is that atoms in a crystal lattice do move. Okay, so you got to think about that whenever you're looking at these notions that things are solid and they're just standing still. They're saying, no, the electrons are vibrating, and maybe the atoms are vibrating as well, so these things vibrate, and that's what they want to show you in general terms, that this is even if it's a solid, it's not standing still. Remember, what is the duality? That it stands still while it moves. Okay. So here we have an example of that, which I showed a couple weeks ago, the phonons. What is a phonon? Well, it's a bunch of atoms that move in some kind of way. So they have all these notions, these phenomena that they call phonon, the particle of sound. It gives you a sound of some kind, and so they track it by sound. We had the the photon is the particle of light. We had the chronon, it's the particle of time. We have the Higgs, the particle of mass, and now we have the phonon, the particle of sound. So they've created all these notions out there. Can they explain any of them? No, they can't. They just say all these move in the crystal lattice in some way that they can measure, that they can detect. Okay, so we know that these things aren't stuck. Okay, at least this is the theory, that they say, these atoms, these electrons, they're moving around, they're vibrating. It's not like standing still. Even though you got a rock, a crystal that's looks solid, the atoms in there are not standing still, okay, or the electrons. Okay, so that's the starting point. And so what did Mossbauer come up with? Well, here it is. Give me a second here. Let me put this up here. Okay, this was Mossbauer in 1958. He came up with it, the Mossbauer Effect, or recoilless nuclear resonance fluorescence, is a physical phenomenon discovered by Rudolf Mossbauer in 1958. It involves the resonant and recoil-free, emission and absorption of what? Gamma radiation. They're going to talk about gamma rays. Gamma rays are high frequency, ultra high frequency rays. Okay, it's important to keep that in mind. By atomic nuclei bound in a solid. Okay, so there is no recoilless emission. So even though there you see them vibrating and so on, and the light, I put it as a wave here, goes outwards, there's no, the atom itself does not recoil, at least for the gamma rays. Okay, that's what he was able to measure. He got a Nobel for that. Okay. It turns out that we have this idea that it's more like this. Okay, that the atoms are not vibrating. We think of it that way. Okay, and again, we're talking about gamma rays here. Okay, so it's important to keep that in mind. We're talking about very high frequency light. Okay? What was this good for? Well, a couple of years later, we had these pair of people, Pound and Rebka, and they ran the Harvard Tower experiment, in which they toyed around with this phenomenon, and they were able to prove what it says there, the last classical test of general relativity. They were able to verify it. Okay, what they saw essentially was that light coming out of the basement. That's where Rebka was, going to the tower at Harvard, where Pound was. It had a different frequency in just I think it's just 3 stories high, maybe a little more. Maybe it's, I don't know how big, how tall the tower was. One was in the basement, the other guy was in the tower. And what they said, the guy from the bottom shot the light, and the guy on the top noticed that the frequency changed. Each one measured his own frequency. It says the frequency changed, and the wavelength got longer, essentially. Okay, lower frequency at the top. And so they said gravity is pulling on light. So they confirmed that gravity bends light with that, essentially. Okay, it warps light. So yeah, it's got to do with it's the gravitational redshift experiment. Redshift meaning, again, it's a Doppler type effect. Okay, whether if it's coming towards you, okay, it's blue shifted. If it's receding, it's red shifted. And so they're saying it's a redshift experiment. The farther light is from you, from the source, the more redshifted, the more the links, in the case of the rope, are farther apart. In other words, the wavelength is longer, okay, or the frequency is lower. Okay, measure the change of frequency of light moving in a gravitational field. Okay, so in other words, the gravity is pulling on light. That's what they said. Frequency blue shifted towards a higher frequency, and test demonstrated the general relativity prediction that clocks should run different rates in different places of a gravitational field. All this as a consequence of Mr. Mossbauer. Turns out that Mossbauer got his Nobel, but these fellows did not. And they proved the last classical thing from general relativity, which is quite interesting. You know, they didn't even get a mention. Well, they did get mentioned, but they didn't get a Nobel. Okay, so what I like about Rudolf is that he was a professor, several universities in the States and in Germany. He's originally from Germany. And this is what he would tell his students. Otherwise, he wouldn't pass them on the test. He was quite strict with them. He said, explain it. Explain it. The most important thing is that you are able to explain it. Yeah, love it. Thank you, Rudy. I'll call him Rudy. You will have exams. There you have to explain it. Okay, he asks his students to explain it. Great. Eventually you pass them, you get your diploma, and you think, that's it. No, the whole life is an exam. You'll have to write applications. You'll have to discuss with peers. So learn to explain it. You can train this by explaining to another student, a colleague. If they are not available, explain it to your mother or to your cat. Okay, so Rudy says, you got to explain it. Otherwise, I guess he's saying you're not a physicist, a scientist, or whatever. Totally in agreement. Did Rudy explain it? I mean, he discovered the Mossbauer effect. Did he explain it? And the answer is no. He had no clue why that was the case, why the atoms did not recoil. Because you would think that, you know, when you shoot a cannon, shoots a ball, which is the quantum version of how light is created and expelled from the atom, because light has origin in the atom. Well, here, if you take a cannon and you shoot it, well, the cannon will go backwards. And so if the photon is energy and energy is mass, you would think that, you know, there's this recoil. And Mr. Mossbauer says, no, there ain't, but he cannot explain why there is no recoil. He just says, it is so. It's another one of those it is so discoveries of quantum. Okay, the first problem that Mr. Mossbauer had to, in other words, the first thing he should have explained really is why we have springs, these notions that all atoms are interconnected, and there's like um, a spring that's acting between the atoms, because that's what a lattice is. The crystal lattice has atoms, but the atoms are, separated from other atoms, and there's something in between them because they are able to maintain this rigidity, this more or less rigidity that you see in crystals or rocks or whatever, okay, metals. And here's a testimony from several sources. Okay, and I want you to look at this. It says, one guy, Disney, says, but the electromagnetic theory is not based on action at a distance, as was Newton's. Space is thought as being threaded throughout with electrical and magnetic tensions, whatever tensions are. Okay, really what he's saying is space is like it's threaded throughout. Next guy, this is Ebbing. He wrote his general chemistry. Chemical bond acts like a stiff spring connecting nuclei. As a result, the nuclei in a molecule vibrate rather than maintaining fixed positions relative to each other. Again, he got that from essentially from Mossbauer, right? The notion that they maintain fixed positions and there is no recoil when they shoot out this energy they call light. A field in physics may be envisioned as if space were filled with interconnected vibrating balls and springs. That's the Casimir effect. And then there was a paper out of this electromagnetic wave physics 2000 at the Colorado University, and folks write over there, wiggling one charge causes the field lines attached to it to wiggle, and after a time the other charge starts to wiggle. It's just like a rope connecting two rocks. Yeah, that's what it looks like. That's what these people are describing. Two atoms connected by a rope. The wave here consists of wiggling line of electric force, which you can think of as being attached to the vibrating charge. I mean, how much more evidence do you want than all this testimony? These people are telling you that atoms are interconnected. You have to think of them as if. Well, now, why not go the whole, mile and say, well, what if they are interconnected, physically interconnected? Because they never identified what they say interconnects them, that acts like a stiff spring, that vibrates, etc., etc. What are they talking about? What is that thing that they say that you have to assume as that it's there as if they were connected? They're all saying the same thing. They're threaded throughout. It's like two rocks connected by a spring or whatever. What are they talking about? What is that entity that connects the two rocks, the two atoms, the two whatevers? And, again, they do the math. They say, like in the case of entanglement, this particle here affects that one over there. The math is great, no problem. They measured, they've got it down pat, but can they tell you what that physical entity that's sending the message to the other particle is? They never identified it. Is there such a monster in quantum mechanics? No. The answer is no. You can look up the standard model. You won't find that mediator even mentioned. It's not. That's when they talk, when they give you the physical interpretation, they throw that in there and say, assume that it's as if. But you don't see it anywhere. And so that's what you have to ask them. Say, well, what is this thing that interconnects the atoms, that vibrates, that does all this stuff? I mean, if it vibrates, hopefully it's a physical object, right? What's vibrating? Concept? Okay, it turns out that they had an answer for many years already. It comes from Mr. Einstein. Okay, Einstein wrote in 1905 his paper. His paper is on the electrodynamics of moving bodies, okay? And what did Einstein say? Well, he said, light is always propagated in empty space with what? A definite velocity, little c there, okay? Which is independent of the state of motion of the emitting body. He's saying that light is independent of the motion of the source. And again, you've heard of that maybe, where a train What happens if you turn your flashlight or your car's driving down the road and you turn the flashlight? Should you add the speed of the car to the light? And the answer is no. But Einstein could not explain it. Again, he could only tell you it is so. That's mathematical physics for you. They tell you it is so. And we can predict that it's going to happen again and again and again. Yeah, great. So far we have a description. Tell me why. What's causing that? See, under the rope, there's no problem because you're moving through the rope, through the ropes, many gazillions. You're moving through, let's talk about one. One atom is moving, one hydrogen atom is moving through the rope, and the rope is forking out at the electron shell and going over and forming part of that shell momentarily and then continues going. So what you have is a bubble made of threads, and one thread, the one from that specific rope, is going around the atom. So the atom can never touch the rope, it's just going through it. And that's why when it pumps back and forth, giving signals along the rope, it's not adding its velocity to the rope. It's just whatever expansion and contraction it does, that's what's going to determine what the frequency or length of the rope is. It's got nothing to do whatsoever with it pushing the rope, which is what people think when they're saying, if I turn the flashlight on, well, I'm on a train or in my car. So yeah, you don't add the speed to the signal called light, because the threads, the two threads that form the rope, go around the atom as the atom moves along the rope. Okay, just like sliding beads on an abacus. Does the bead push the wire along which it's sliding? And the answer is no. And so no, you don't add the speed of light to the motion of the source. And he never figured it out. He said it is so, but he could not explain why, the physical cause of that. Okay. So what's the issue? The issue is that here's again Mossbauer's recoilless emission. We're saying that the atoms are not moving in this case as gamma rays come out of there. How did we do it in under the rope model? Here you have it side by side. Okay, we have it with a rope. Okay. So the atom does not have to move at all. If you move that, let's assume that's a cube, a crystal of some kind. If you move it, it's just going to eat into the rope. It's going to slide along the rope. It's not going to push the rope, in other words. Okay? And why is, again, the frequency of light the same? It doesn't change. Well, here I think I've explained this in the past. Here you see it. That what you have is that all you're changing as the atom is expanding and contracting, what it does is just torques the rope at different rates. By doing so, the rope does not have any chance of going faster. All it can do is change the frequency for the wavelength, in this case the link length. Okay, so there you see 8 links, for example, in the top one. And if the atom is pumping slower, then you're going to have 4 links. And if it's pumping faster, you're going to have 16 links. What changes? Well, the length of the rope, the physical entity that mediates light, is the same in all cases. You have the same 1 meter or whatever amount of rope. What changes is just the number of links produced by that amount of rope threads. So this is the answer to Einstein's question, but it also answers Mossbauer's question of why there is no recoil. There's no recoil because there is no push, okay? Especially for gamma rays. It turns out that these people, they are not able to measure exactly the gamma ray. So the party line today is that Well, we can't measure so much at that frequency, and so what they say that essentially there's no recoil because they cannot really measure at that level. Okay, and so they do a mathematical calculation, and that's it. But again, they have no physical interpretation for their calculation or for their measurement. They don't know why that's the case. Okay, so this is where we have differences with these folks. Okay, what are the conclusions? Let me go through them here. Recoilless emission is just another unjustified discovery of quantum mechanics. They have discoveries, they have no explanations. None whatsoever. Mossbauer never identified the springs that vibrate between atoms and holds them together in the crystal lattice. What is that thing? What is that spring that holds two atoms together or that keeps them apart or whatever? They never identify that. They just say you have to make believe that it's there. It's like it's as if it were there. Why not just say it is there? Okay, because you can't see and touch it. Is that the reason? Mossbauer never explained what causes the effect named after him. Okay, he never could explain the Mossbauer effect. He just described it. He says it is so. Einstein never explained why light speed is independent of the movement of the source. Okay, so we have all these unexplanations. No one can explain what he discovered. They all get Nobels, they all get their names in lights, but not one of them can explain what's going on. Okay, and the rope model merges Mossbauer effect with Einstein's principle of relativity, which is the constancy of the speed of light. And light always torques at the same speed along the electromagnetic rope. Why? Because frequency is inversely proportional to the length of the link. You make the links smaller. I always show that in my rope. Let me get this one out of here. Here you have the rope, okay? And the more you torque it, the more links you have. The less you torque it, the longer the links and the fewer links you have. That's why the speed of light is a constant always, okay, in every situation. And that's why we have recoilless emission, and that's why Einstein could not add the speed of light to the movement of the source, because he was thinking push, and he could not explain why it wouldn't be so, why you don't have to add it. And the answer is that the atom goes right along and slides through the rope. So it has no reason to push it, and it doesn't. Okay, so there you have an idea on Mr. Mossbauer and his effect, which he could not explain. Okay, moving on here, let's move on to the questions and comments that people made. Fellow says, do a video on the modern transistor and how companies test each of the 1 billion individual transistors. Well, they don't really test, they test certain bus lines, etc. Okay, but I think the main one is, how it works, how transistor works. And we're not interested in technology here. We try to answer the scientific questions. And scientific questions are explanations of mechanisms. And there's already a video out there, several videos really, that show you how transistors work, okay? Look that title up, Transistors, How Do They Work? And you'll find good explanations of how these transistors work. The one on the top is a bipolar, the one on the bottom is an MOS. I work with both technologies. Started out with bipolar, worked my way up to MOS, metal oxide semiconductor. And yeah, I mean, you'll find the explanation of how they work. The important thing that you have to keep in mind is something else. This is what's important, at least if you're going to watch these videos. This is what you got to keep in mind. And that's, here's a silicon lattice, okay? And what you have is, this is just pure silicon, assuming it's not contaminated in any way. And what you have is, and we're going to use the quantum version here so that I don't take you into the complexity of the rope model. Well, we're just going to use their model because for what we need to explain here, it's fine. You have 4 electrons on the outer shells, okay? And so when you have 4 other atoms around you, you have all those uh, outer shells completely covered with 8 electrons, which is what they say is needed for it to be saturated. And so silicon is just all saturation, no problem. It's a semiconductor because of that. It doesn't conduct electricity. How do you get it to conduct electricity then? Well, you have to do something to it. You have to dope it. It's called doping. Usually the typical ones are boron and phosphorus. Phosphorus is negative because it has an extra electron, and boron has 1 fewer electron. That's why it's called positive. Okay, one has 5, which is boron, and boron has 3 in its outer shell. Okay, so if you put phosphorus into the silicon lattice, there's going to be 1 electron that doesn't know where to go, and supposedly that's the one that's going to drift and cause the electrical properties. And if you put boron, what you have is you're introducing holes. You're introducing the absence of an electron, known as a hole, and now you have current because this electron goes to try to fill that hole, but it leaves a hole behind, and so that you have the movement of holes in the opposite direction of the electron flow. That's the theory, okay? And so here you see it. You see boron and phosphorus, okay? Phosphorus at the top. You can see it's got an extra electron, which I marked in red, okay? And so it tends to move around, okay? Boron, on the other hand, it's missing 1 electron in its outer shell. I put a little circle, elongated circle there to show that, you know, it's missing that electron. And you can see that they have a different, the atom itself has a different structure. The ones on the right are the structures that we propose under the rope model, okay? And chemistry uses those, calls them balloons. Well, they don't call them balloons, they call them orbitals. They call them energy levels. No, they are balloons. They are physical balloons, but chemistry never figured that out because quantum mechanics says that that's just a little bead going around. No, those are balloons, and that's exactly the model that we have in under the rope model. Okay, so what you're seeing there is the real McCoy. Okay, okay, give me a second here. Another question, first asked. It says, no need for parallel universes. Use a torus link of 2 threads to qualify existence. The issue here is the word exist. What does the thread exist? The single thread that we have in under the rope model. Does that exist? And the only way we can get it to exist if there's another thread, another universe, parallel universe out there that is in which none of the atoms of that universe are connected to any of the atoms in our universe. Okay, so then we can say that our thread exists because there's another thread nearby, and all we have to have for existence is location. Location, what is it? Set of distances, and here we have a distance between the 2 threads. Okay, so he says a thread turns into our universe by playing cat's cradle and crossing over itself skillions of time to make atoms. This is not possible with a thread loop after you twine it into a rope. Okay, a twine thread loop has 2 ends, and cat's cradle possible. No cat's cradle possible. If you insist on using a single thread, then use a torus knot, which is functionally the same thing. Well, cat's cradle is a game that people play there. Try to make patterns with those strings or threads or whatever. And I think this guy got his fingers tied up there, tied up in knots. I don't think he got it right. I think you can do it with a single thread. Okay, we don't need to do any of this that he talked about. I'm not sure what he's not understanding. Here's my version. Okay, here's a twisted thread, closed loop thread. It's a rubber band. Okay, and that's a picture I took. Here's the real McCoy. Let me get this one out of here. Okay, here's the real McCoy. I did that one. I just took a picture of that. So you can see that it's possible to take a rubber band, closed loop thread, right, and twirl it into a rope. Okay, and it's closed loop. In other words, you can do, if the thread is big enough, whole universe. Uh, you can move around from one point all through that thread, everywhere you go, through the atoms, through the ropes, and eventually arrive at your starting point. So I'm not sure what this fellow is not understanding. Why he needs two threads, first of all, I don't understand that. What his problem is. I really can't understand his problem. Okay, another fellow asks a question. He says, does light bend around other heavy objects, not only stars? Can you explain a little more about this bending? Does mass have anything to do with it at all? And the answer is right there in front of you. It's really very simple. You just have to understand what relativity is proposing, which is mass, a concept. It's like weight. And you put weight on top of a canvas, which is not a canvas, which is space-time, which is a concept. So you put the concept weight on a concept called space-time and you bend it. That's what these people are saying. We're done. That's it for general relativity. If you wanted to know the relativity theory, there it is. That's all there is. Don't look beyond that. That's all there is. That's the theory of relativity. They say it's their equations, but equations are not theories. Equations are descriptions. Theories are explanations. That's the explanation they give. So that's the end of general relativity right there. They have one concept bending another concept. How do we do it? You got to look at it as a roulette there. The little ball going around in circles. And that's essentially what they're saying that the Earth does around the sun. It moves around a roulette, a canvas that was created by the weight of the sun on that canvas. How do we do it? We say much simpler. You twirl around, the sun twirls the Earth around at the end of gazillions of threads, ropes. We're done. That's it. Essentially, here it is. I showed sometimes. That's why the Earth doesn't fly out of the sun. My fingers are the sun, and the ball is the Earth. That's how simple gravity is. We're done. That's it. And here you see, I show the four mechanisms. Okay. To summarize all that, essentially you have particles, which is what Newton suggested. Okay. And you have, you could do it with pressure there on the right hand side. I'm not sure too many people suggest that. I'd like to see them form a perfect and constant elliptical orbit of the Earth by applying all these particles coming from everywhere. Okay? But the ones that we're comparing really are the two on the bottom. You have warp space, which is what Einstein proposed, okay? And you have the rope model, which is every atom on Earth is connected to every atom of the sun, and the sun essentially just twirls the Earth around like a kid would twirl a ball at the end of a string around his head. And because space is nothing, the Earth doesn't have anything to rub its elbow against, so it can keep doing this forever almost. Okay? So there is no resistance, no friction between the Earth and space, and that's why we roll around the sun. That's how simple it is. Okay, so I'm not sure we need to do much more on that than what I just explained. If you have any questions, ask me, but that's it. It doesn't get any better than that. Okay, fellow asked something about location. He says, what do you mean by location? I thought everybody knew. Your distance from every other object in the universe and angle. Well, I don't know about the and angle part. That's not at all. It plays no role whatsoever. But yeah, the distance from every object in the universe to the target object. And that's what you see there. You see a cube, and you have a distance to every single object in the universe. That's called location, the location of the cube with respect to all matter in the universe. We're done. That's the definition of location. So I don't know if he agrees with it or what, but I just wanted to clarify that that is what we call location. Same fellow says something about squares. He said, you can't use the word square on the subject as the subject of a sentence. And yeah, he's right. In physics, okay, so in ordinary speech you can use anything you want, but in physics you cannot use the word square as a subject of a sentence. He's totally correct. And the reason is that a square is an object that does not exist, and physics only deals with objects that exist. That's why you can't use it. Okay, now he says exist means it has to have location. Yeah, exactly. That's what exist means. Means that if it doesn't have location, it doesn't exist, and if it doesn't exist, it's not a part of physics. That's irrelevant compared with regard to the question of what is the definition of the word object. See, what people have done for many years is confuse the word object with the word exist. They think it's a synonym. And so this fellow makes the same error. He thinks that because a square doesn't exist, because a square doesn't have location, you should not be able to use it in physics because it's not an object. No, it's an object, but it's an object that does not exist, and physics only deals with objects that exist. That's the answer to that question. Okay. Okay. Next question, I think same fellow. He comes up there and he says, does light have shape or not? Yes, it does. We know that it's a rope. Yeah, and a rope has shape. I don't know any rope that does not have shape. This one has shape. I hope you can see it. All ropes have shape. I don't know any rope that does not have shape. So yeah, light has shape, but we don't say it that way. We say that the mediator of light has shape. Light is a combination of two things: the thing and its behavior, the object and what it does. The thing is a rope. What it does is torque. And so when we say light, we're really putting both together and saying light is a rope that torques. That's what light is, okay? And actually it's the thumping that it gives the atom, for example, in your eye. It's that thumping that sends you the signal to your brain through other atoms. It's relayed. So yeah, light is a rope, so a rope has shape, and it exists because it has location. But the important thing is that light is a rope, but the correct way of saying it is light is mediated by an object, and that object looks more or less like a rope. It has a rope-like configuration. It looks like DNA. Okay? What it does is torque. Okay, that's why hopefully light moves. Okay, there is some motion there. Otherwise, we'd have a static universe. Okay, fellow says, what do you mean torsion is bidirectional? I twist the clothesline from one end, and so do atoms. Okay, tell me, don't do it from the ends. You're getting confused when you do it from the ends. Do it from the center. Okay, now tell me that torsion there, that thing that's twirling around there, which way is it going? Is it going right or going left? What atom is it stimulating? Well, I would say it stimulates both atoms at the ends. So yeah, this is totally different than what the mathematicians have, which is just going in one direction. The waves come out of the atom, go in one direction. Why would they come back? And particles, if you want to do particles, same thing. It comes out of the atom, goes in one direction. This one, since it involves two atoms, it interconnects two atoms. It's a torsion that propagates to both atoms simultaneously. You go to one atom, you see it's torquing there. You go to the other atom, it's also torquing there. In fact, from one atom's point of view, it's going clockwise. From the other one, it's going counterclockwise. Okay, so yeah, I'm not sure what problem he has. This should be straightforward. Okay, and final issue here says, why should the amount of links eaten by an atom during expansion correspond at all with link length? Well, the issue here is that I didn't invent this. Mother Nature invented this, okay? Mr. Bohr, Niels Bohr, he's the guy who proved, if you want to use that word, 1911, that photons. Well, let's say it in reverse. That an electron falls between energy levels. It doesn't fall to an intermediate energy levels, and that energy level is the amount of energy of a photon. The amount of energy of a photon under the rope model is one link of a given rope. Okay, it's one link. That is your photon. That is your energy. And so what we're saying is that when the atom expands, it eats exactly one link. Okay, I didn't invent that. Mother Nature. That's like saying, why is the speed of light, little c, 300,000 kilometers per second? I didn't invent that. God invented that, or the devil, or one of those guys out there. All we can do is measure and say, yeah, that's the speed of light, 300,000, and it's a constant. Then you got to explain why it's a constant. But why is it specifically 300,000 kilometers per second? Well, maybe in another universe that has more matter, or more thread, or less thread, or whatever, they have a different speed of light in that universe. That could happen. Also, the speed of light could be different on the other side of our universe. I mean, I haven't been there. I don't know. I can only tell you what's in this neighborhood. And similarly, all we can say is that if Mr. Bohr has it right, mathematically right, and he says that a photon is the amount of a single photon, the energy of that photon is what determines the difference between gaps between the one energy level and another energy level within which the electron falls, and it doesn't fall anywhere between those two energy levels, then it's very clear that under the rope model, you have to eat one rope, because that's what's going to determine the outer expansion and the inner expansion, and nothing in between. Okay, so that's the notion there. And with that, I'll see you on Sunday. We'll see you then. Bye-bye.